Hello, pirates. Today we will look at the ways to determine the formulas and names of ionic compounds that have transition metals. As you recall from our last unit, transition metals are located at the center of the periodic table. What makes transition metals different from alkali metals, alkaline earth metals, and other metals is the fact that they have multiple charges that makes them stable, as opposed to the predetermined number of electrons for other metals. So, whereas an element like sodium always has a charge of +1, calcium always has a charge of +2, and aluminum always has a charge of +3, transition metals can have multiple charges. Copper can form a +1 or a +2 charge. Iron can form a +2 or a +3 charge. And manganese can form anywhere from a +1 to a +7 charge, though the +2, +4, and +7 variations are the most common. So, why is this important? Let's take a simple compound like table salt or sodium chloride. As we've learned before, we write out the element symbol with a charge. So we have Na+1 and Cl-1. We can then do the crisscross method, and knowing that we drop the plus and the minus signs and do not write the number ones, we get a chemical symbol of NaCl. Now, let's do the same for a compound that contains a transition metal. Here's rust, which is an iron oxide compound. But if you recall from earlier, iron can have a charge of +2 or +3. So how do we know which one it is? Well, when you are given a transition metal, you will know its charge by its Roman numeral. If there's one big takeaway from today, it's that charge of an ion equals the Roman numeral that follows the element's name. For example, let's look at two variations of copper and iron. If you have Cu+1, then you write the name copper Roman numeral 1. If you have Cu+2, then you write the name copper Roman numeral 2. For iron, if you have Fe+2, you write the name as iron Roman numeral 2, and if you have Fe+3, you write the name as iron Roman numeral 3. This seems simple enough, but it's one of the easiest things to forget come crunch time. So come the day of the test, remember, charge equals Roman numeral. So if we go back to our example of rust, we can now see that it is incorrect to write the name iron oxide, because iron comes in two charges, the +2 and the +3. In rust, iron appears in the form of the +3 ion, so we have iron Roman numeral 3 oxide. Like we've done with other ionic compounds, we write the ions for both the cation, which is Fe+3, and the anion, which is O-2. Note how we have a Roman numeral 3 and the charge is now +3. We then crisscross and get a formula of Fe2O3. So some of us are wondering, why bother doing this? Is there actually a difference between the variations of these transition metals? When we look a little bit deeper, we find out that these ions make compounds that both look and react differently than their ionic cousins. Iron 2 sulfate is a light blue color, while iron 3 sulfate has a dark yellow hue. Tin 2 oxide is black, while tin 4 oxide is white. And finally, copper 1 oxide is red, and copper 2 oxide is dark gray. Even though each of these pairs is made of the same two elements, they combine in different ratios to make very different compounds. Let's take a look at how to write a formula when given a compound's name. Now, before we start, we need to look at a few exceptions to our transition metals rule when it comes to using Roman numerals. Even though they are both situated in the transition metals area, silver and zinc both only have one charge. Silver is always +1 and zinc is always +2. This means it would be incorrect to use Roman numerals when using either of these two elements when writing out compound names. Conversely, we have two elements outside of the transition metals block that do require the use of Roman numerals because they exist with multiple charges. Tin and lead both take either a +2 charge or a +4 charge, despite being in a column that is labeled +or -4. And although I find it easier to commit these examples to memory, these examples are on your ion list on the back of your periodic table. There are a few other examples of metals that don't conform to the pattern we've discussed, but for the sake of this course, these are the only 4 exceptions you need to know: silver, zinc, tin, and lead. So let's take a look at a few examples. This is the compound iron 3 chloride. Since iron has a Roman numeral 3, we know the charge on the Fe is +3. Note the similarities. And we can find chlorine has a charge of -1 from the periodic table. Then we crisscross the charges, remembering not to bring down the plus or the minus signs, and remembering that we don't write 1 as subscripts, giving us the formula of FeCl3. Next, we have the compound copper 2 oxide. Since copper has a Roman numeral 2, we know that the charge on Cu is +2, and we can find that oxygen has a charge of -2 on the periodic table. Then we crisscross the charges. However, after we crisscross the charges, we see that both the subscripts are the same. Now, one of the limitations of the crisscross method is that if you have 2 numbers that are the same or have a common factor, then the numbers must be reduced. Since both of these numbers have a common factor of 2, we can divide both by 2, and we get Cu1O1, but since we don't write down the ones, we simply get CuO. And finally, we have the compound silver sulfate. Remember, silver is always in the form of a +1 ion, so there will be no Roman numeral next to the silver name. If we look up sulfate on our ion list, we find that it is SO4 -2. When we crisscross, we get the formula Ag2SO4. And finally, we have our more difficult task of going from formulas to names. So let's take a look at an example of Cr2O3. Now there are 2 different ways to write the name of this compound, and both are equally acceptable. The first way is to use the reverse crisscross. When we write normal ionic compounds and their formulas, we do a crisscross to figure out their formulas. So when we have a Roman numeral that we don't know the charge of, we can reverse crisscross, basically reverse engineering, to figure out what its charge should be. So we have the formula Cr2O3. So now we have to take the 2 from the Cr and make it the superscript of the oxygen, and take the 3 from the oxygen and make it the superscript of the chromium. So we get Cr3O2. But remember, these have charges, so the metal will be Cr+3, and then the nonmetal will be O-2. Now remember, when we crisscross, like we said earlier, one of the limitations is that sometimes we have to reduce based on common factors. So what we do to check for that is we check the charge of the nonmetal or the anion. So we ask ourselves, is -2 the correct charge for oxygen? If we look at our periodic table, it is. So if -2 is the correct charge for the oxygen, that means +3 is the correct charge for the Cr. And then Cr is chromium. So our compound name is chromium Roman numeral 3 oxide. So the other method is the balancing charges method. So we start out with our same formula, but this time we're going to make a little chart, an upside down T, if you will. And what we do is we write out the 3 oxygens and the 2 chromiums based on the subscripts. So what we're going to do is we're going to take a look at the negative side first, because like we said before, we always know the charge of the negative ion. Each one of these is a -2 charge, and there are 3 of them. So in total, they add up to -6. Now for all ionic compounds, you have to have a neutral charge. So if you have a -6 worth of charge for the anions, means you have to have a +6 worth of charge for the cations. And they have to be distributed evenly. So if you have 2 chromiums that add up to positive 6, that means each one has to have a positive 3 charge. So just like before, we take that positive 3 charge and we write it as the Roman numeral, and we have chromium 3 oxide. Note that both names are the exact same, even though the methods are a bit different. Next, we have the example of CuSO4. So let's try the reverse crisscross method. We have CuSO4. The problem is when we look at this example, it doesn't look like there's a subscript for the Cu, and it looks like the subscript for the SO is 4. However, we have to remember that if there is no subscript in the example of the Cu, we assume that it's 1. And SO4 is a polyatomic, so we have to keep that together. So it means that there's only one of the SO4. So the way we would actually write it would be Cu1 parenthesis SO4 parenthesis 1. Now we would never write it this way, but for the sake of the reverse crisscross, this is the way you need to think of it. So what we do is we reverse crisscross, we bring the one up to the Cu, and we bring the other one up to the SO4. So we get Cu1 SO41. Then we have to remember to add our positive and negative charges, which gives us Cu plus 1 SO4 minus 1. So just like before, we have to check the charge of the anion, the minus 1. If we look on our ion table, we find that this is an incorrect charge for sulfate. Sulfate actually has a charge of minus 2. So we have to ask ourselves, what happened? Well, in this case, this example, this formula was simplified by a factor of 2 when it was named. So what we have to do is we have to unsimplify it by multiplying it by 2. So if we multiply both sides by 2, we get Cu plus 2 and SO4 minus 2. If we look at the charges, they are now correct for the sulfate, which means we're now correct for the copper. So we can write the correct formula, copper, Roman numeral 2, sulfate. Let's take a look at the balancing charges method. So here's CuSO4 again, and we make our upside down T. Now we only have one sulfate, and we only have one copper. If we look on our ion list, we can figure out that its charge is negative 2. So the total anion charge is negative 2, which means the total cation charge has to be plus 2. Since there's only one copper ion, we know that that copper has a plus 2 charge, which means we get the same formula of copper, or the same name of copper, Roman numeral 2 sulfate. And our final example is Zn3PO4. Now, if we look a little bit more closely at that, Zn is the element zinc. If you recall from earlier, zinc is actually one of our exceptions. So we don't need to use the reverse crisscross method, and we don't need to use the balancing charges method, because zinc does not require a Roman numeral. So all we have to do is simply write the name of the cation, zinc, and the name of the anion, in this case it's a polyatomic and the ending doesn't need to be changed, as phosphate. One of the trickiest things about using Roman numerals is that you think you always have to use them. Remember, you never use them if the metals are in a family that have a charge that's always determined, like the alkali metals, the alkali earth metals, or elements like aluminum. And you also have exceptions like silver and zinc. So that's it. That's all there is to writing formulas and names using Roman numerals for transition metals. Have a great day, Pirates.